Okay, following the previous discussion on graphs of functions, let's see if we can go through these 10 problems together. Here we're interested in drawing a graph of a function y equal to x plus 3. So our x is running from negative 2 to 4. So I'll say x here minus 2, minus 1, 0, 1, 2, 3. I'll put my 4 there and check the corresponding y values that we'll get. So there's my y. Let me change my color to black to say if my x is minus 2, so it's minus 2 plus 3, it gives us a 1. And if our x is minus 2 plus 3, that's 2. And 0 there is 3, 1 there, 4, 5, 6, 7. Then I'm moving to my Cartesian plane because I want to do this drawing. So what I'll do is I'll have my x here and y. Now, what's of interest here is to note that x is running from negative 2 up to positive 4. So I'll say 1, 2, 1, 2, 3, 4. So that's negative 2, negative 1, 0, 1, 2, 3, 4. What about our y? Our y is running from 1 all the way to 7. So it's 1, 2, 3, 4. I think it will proceed in that fashion. 1, 2, 3, 4. Then what do we do with these points? We're going to plot them. Minus 2 and 1. Minus 2 and 1 is this point there. Then minus 1 and 2. Minus 1 and 2 is that point there. 0 and 3. Goes on like that. So when I take my blue pen, I see that this falls on a straight line. So I can label it y equal to x plus 3. That's drawing. Then next we are drawing another graph again, and we want to state its gradient. So this one here, we can just look at special points. Let me go to the Cartesian plane and say, because I can see that it's linear because the highest power there is 1. So I put my x, I put my y. So what I'll do is I'll test to say, but when x is 0, what will be the value of y? So when x is 0, it means my y is minus 1. So 0 there, minus 1, minus 2, minus 1, minus 2. What about when y is 0? When y is 0, we have 0 equal to 2x minus 1. And when I do so, I'll get my x equal to half. So I can move there to say, but this is 1, this is 2. So for my y, I'm interested in minus 1 there. So minus 1, maybe proceed to minus 2. I can have here 1, I can have 2. Now, I'll just target these special points to say, but when my x is 0, y is minus 1. So whatever we do, our graph will pass through this point. And when our y is 0, x is half. So x is half somewhere there. Then I'll take my blue pen and join those 2 points like that. Then I can label that this is y equal to 2x minus 1. They are saying state the gradient. Gradient, we saw it earlier that gradient denoted by symbol m. M is equal to coefficient of x, which is just 2. Then moving on, complete the table and draw the graph of y equal to x squared. So I'll do my template for the table. We're interested in minus 3 to 3, x, y, minus 3, minus 1, minus 2, minus 1, 0, 1, 2, 3, something like that. Because we want to use table of values, we're going to be doing little substitution there. So we say minus 3 squared, it gives us 9. Minus 2 squared gives us 4. Minus 1 squared, 1. 0, 1, 4, 9. So it's clear that our graph is symmetrical. And when I go to my Cartesian plane, I'm going to have here x, y. Let me pick a different color to say, but my x is running from minus 3, 1, 2, 3, and 1, 2, 3 for positive. Then my y is running from 0 to 9. So it's 1, 2, 3, 4, going all the way up there. And so I can now bring in minus 1, minus 2, minus 3. I can have 1, 2, 3. So there is 1, 2, 3. Well, I can double the vertical point so that at least I try to fit in a bit to say, but let me make this 2, 4, 6, 8, like that. Then let me bring a different color to plot to say, but when I have minus 3 for x, minus 3, my y is 9. So somewhere up there, that's where I have the point. Then next is minus 2 and 4. Minus 2 and 4 at least is there. Then next I have minus 1 it will give me 1. So somewhere in between there. Then 0 and 0, it means it passes through the origin. 1 and 1, somewhere there. Then I have 2 and 4, 2 and 4 there. Then I have 3 and 9, somewhere that side. So now if you can follow through clearly, you can see that this is a symmetrical curve about that point. Then we put the equation that this is y equal to x squared. I think you can see that inverted U shape, we call it a parabola. Then draw the graph of y equal to x squared minus 1 and estimate its roots. So when we draw such a curve, I'm just going to do the sketching. I'm not actually drawing. I don't need table of values because it's similar to what we've done before. We're just dropping it 1 unit downwards. Instead of it turning at this point, it will turn at a point where y is minus 1. So this is our y, this is our x. So the rest is the same. So I'll just try and repeat the same pattern. Then I say y is x squared minus 1. So if I had proper calibrations there, I'll be able to estimate the value. But now, if we want to do it algebraically, we are saying x squared minus 1 will be equal to 0. That's when we are on the x-axis. So x is plus or minus 1. So we are assuming that if that was done properly, this point and that point should correspond to minus 1 and positive 1. Then next, we are interested in sketching. So we are sketching the graphs of y equal to 2 over x. So now what we'll do is we just target the numerator there. So if we look at the numerator, this numerator is positive 2. So our graph, it will exist in two parts. That's the first and third quadrant. And when I say first, this is the first quadrant, third quadrant. And our asymptotes, which I will redraw in red, are going to be here and there because x cannot be 0, y cannot be 0. Then plotting the curve is anything of this nature. We just go as far as is possible to the axis, but we do not touch them. That's the picture. Then state two properties of reciprocal graphs depending on A, because they take the general form y equal to A over x. If A is bigger than or equal to bigger than, or it can be equal to bigger than 0, then this graph, it exists in two parts, which are first and third quadrants. Otherwise, second and fourth quadrants. So it exists in two parts, and the other one is it has asymptotes. These are lines that this curve cannot touch. Then solve x squared equal to 5 graphically. So here, when we are solving it graphically, we are interested in building up the graph of y equal to x squared and another graph y equal to 5. We are interested in the points where the two meet. So on our Cartesian plane, we'll be looking at something of this nature. That's our x, our y. Generally, graph of y equal to x squared, the parabola taking that shape. So where we have our y equal to 5, we are going to have a horizontal line like this. So our interest is to estimate the coordinates or the points where the points of intersection matches the x-axis. So algebraically, to be having a rough example, this will now be equal to, if I'm to continue with this problem, algebraically, x is plus or minus root 5. So this will be 2 point something minus 2 point, I don't know, something, then here we have positive 2 point something. So as you estimate, you do proper guess of the points on your curve. Now draw the graphs of y equal to x squared and y equal to x plus 2 on the same set of axes. So what we'll do is with x squared, I'm sure we are now familiar with it. It's just a curve passing through the origin and is symmetrical somewhere. But with this one here, we have got a gradient of 1 there. But now one thing we know is the graph of y equal to x squared is a curve which passes diagonally through the origin. So we'll just raise it up 2 units upwards. So where we have y equal to 2, let me draw it in black to say it will be a curve like this. That's y equal to x plus 2. So as we can see clear, these two graphs, they are crossing each other somewhere at 2 points. So those will be solutions to the equations that we'll get from x squared equal to x plus 2. Identify the x-intercept of y equal to. So if I want x-intercept, it means y will be 0. So in the process, it means 0 equal to 3x minus 1, 9. So 3x is actually equal to 9. Therefore, the x-intercept is x equal to 3. Explain why carefully scale choice is important when drawing graphs. This is important to have meaningful estimates when solving problems graphically. So basically that's it for the introduction to graphs of functions for extended mathematics. We'll meet again in the second or last part where we are visiting similar questions to check if there are any variations to the concepts and knowledge we have. Bye folks.